We were discussing about the histogram technique for probability density estimation, and we have considered different cases in one dimension, in two dimension, and we started our discussion in multi-dimension when the dimension is more than 2. So, we have seen that in one dimensional case what we have is a probability density curve. In two dimensional case what we have is a probability density surface, and in both the cases our constraint was that in case of one dimension the total area under the probability density curve has to be equal to 1. In case of two dimension the total volume under the probability density surface that has to be equal to 1, and accordingly we have computed that what is the probability density value on every bin, whether it is in one dimension or in two dimension. So, in case of one dimension our bins are actually the line segments like this. So, if I have variable x and on this axis I plot the probability density function p x, then what we have done is the x axis is divided into a number of bins or number of cells, and within a cell we have assumed that the probability density function is constant. So, it is something like this, where the height of this bar, which is nothing but the value of the probability density within this cell, that is determined by the fraction of the training samples which falls under the bin, and simultaneously what is the width of this particular bin. Okay. So, this h I or h j for a jth bin, which is nothing but p of x, where x lies within this jth bin, which is given by 1 upon w j, where w j is the width of the jth bin times n j by capital N, where this n j is the number of training samples which falls under the jth bin, and capital N is the total number of training samples. So, this is what we had in one dimensional case, or when our variable x is a scalar variable. In two dimension we have extended this concept. So, we have a vector variable x whose components are x1 and x2. So, I have this plane x1 x2, where this is the x1 axis, this is the x2 axis, and a axis perpendicular to this indicates what is the probability x, where x is a vector. So, following the same concept, we divided this plane x1 x2 plane into a number of bins like this, where each of these bin is now a rectangle, and the probability density value over a bin will be represented by a bar something like this, where this bar will have a volume. The volume is given by, if this bin is the ijth bin, so h I j times a I j, where a I j is the area of this bin, and we said that this has to be equal to n I j upon capital N, where n I j is the number of samples which falls under this ijth bin, and capital N is the total number of samples. So, from this we can compute h I j, which is nothing but p of x, where this x is a vector. So, what is the probability that this vector x will fall under the ijth bin? Okay. So, which is given by 1 upon a I j into Nij upon capital N. And here again it is assumed that within a bin the probability density value is constant. Okay. But the probability density value varies from bin to bin. We have extended this concept to 3 dimension, where obviously in case of 1 dimension, as the bins are line segments, in case of 2 dimension, the bins are area segments, which are nothing but rectangles in our case. In case of 3 dimension, the bins will be volume segments. So, it is a cuboid or say parallelogram, things like that. So, in the last class we had taken a particular scenario. So, now my vector x will be a 3 dimensional vector. So, vector x is equal to x 1, x 2, x 3. So, it has got 3 components. So, accordingly I say that this is my x 1 axis, this is my x 2 axis, this is my x 3 axis. So, accordingly I define a 3 dimensional space and every vector is a point in that 3 dimensional space. So, to estimate the probability density function, what I have to do is this 3 dimensional space has to be divided into a number of volume elements which are nothing but the bins. So, in the last class we had taken a volume element something like this. So, here you find that there are 8 volume elements, 4 on this side and 4 on this side. And once I divide this 3 dimensional space into such volume elements, every volume element will have 8 vertices. Okay. So, if I consider a single volume element out of this, so this volume element has got 8 different vertices. The vertices are 1, 2, 3, 4, 5, 6, 7 and 8. So, these 8 vertices uniquely define this particular volume element. Now, we can take one advantage that because this volume element is a rectangular parallelogram, I need not specify all the 8 different vertices. Rather, if I specify only 2 vertices, then also my volume element is completely defined. So, one of them, if I say that this is my x axis or x 1 axis, this is the x 2 axis and this is x 3 axis. Considering this, you find that if I simply specify the coordinates of this volume element and the coordinates of this volume element, that uniquely specify this particular rectangular parallelogram, where the coordinates of this vertex, the x 1 component will be minimum of x 1 components of all the 8 volume elements of all the 8 vertices. X 2 component will be the minimum of x 2 component of all these vertices. X 3 component will also be the minimum of x 3 components of all these vertices. Similarly, for this vertex, you will find that x 1 component is the maximum of x 1 components of all the 8 vertices. X 2 component will also be the maximum of x 2 components of all the 8 vertices. X 3 component will also be the maximum of x3 components of all the 8 vertices. To make it more clear, let us assume that this is an unit cube, and you find that if it is an unit cube and this vertex is at the origin, the coordinates of this vertex will be 0, 0, 0. Coordinates of this vertex will be 0, 0, 1. This vertex will be 1, x2 component will be 0, x3 component will be 0. For this vertex, both x1 and x2 component will be 1, whereas x3 component will be 0. So, it will be 1, 1, 0. For this vertex, all of them will be 1. For this component, I will have x2 component 1, x3 component 1, but x1 component is 0. So, it is 0, 1, 1. For this one, we have already done, and for this, which is hidden, it will be x1 is 0, x2 is 1, and x3 is again 0. So, you find that I have got, this one is left. For this one, I will have x1 component 1, x3 component 1, and x2 component is 0. So, it is 1, 0, 1. So, I have 1, 2, 3, 4, 5, 6, 7, 8. So, all the 8 vertices. Now, if you look at the coordinates of all the 8 vertices, you find that considering the x1 component, the x1 components of all the 8 vertices are either 0 or 1. So, the minimum is 0. Similarly, x2 component minimum is 0, x3 component minimum is 0. So, 0, 0, 0 is one of the vertex which is required to define this volume element, and that is what is this one. Similarly, the maximum of all the x1 components is equal to 1, maximum of all the x2 components is also 1, and the maximum of all the x3 components, that is also 1. So, it is 1, 1, 1, which is another vertex which is necessary for defining this particular rectangular parallelogram, and which is this one. So, if I simply know this vertex and this vertex, I can form this rectangular parallelogram. And because this is the minimum of all the coordinates, so I call this as mean point, and this being the maximum of all the coordinates, so I call this as max point. So, one thing is clear, that if I know the mean point and max point of every volume element, then my volume element is uniquely identified. Now, what is the use of this mean point and max point? We said before, whether it is in one dimension or two dimensional case, that to estimate the probability density function in a cell or a bin. So, in three dimensional case, each such volume elements are the cells of the bins. Okay. So, to estimate the probability density function in each cell or each bin, I need to find out how many points or how many training vectors are actually falling in the bin. Okay. So, in case of one dimension, you find that I know boundary, this minimum boundary of the line segment, I know maximum boundary of this line segment. So, a value of x which is greater than or equal to this and less than this falls under this bin. So, that is my check. How do I find out that how many training samples are falling within the J bin? You come to two dimensional case, every point here also I have, say for example, this bin, this will be the mean point, this will be the max point. So, this mean point has a coordinate x 1 mean and x 2 mean. This is the coordinate of this point, and coordinate of this point is x1 max and x2 max. This is the coordinate of this point. Now, for any point P lying within this cell, I must have say point P whose coordinate is say x1p and x2p. Condition must be that x1p has to be greater than or equal to x1 mean and it has to be less than x1 max. Simultaneously, x2p has to be greater than or equal to x2 mean and it has to be less than x2 max. So, if I simply have the mean point and max point, I can easily determine that what are the samples which falls under which bin, and I can count the number of such samples. So, the number of samples falling under the jth bin in case of one dimension will be nj, and the number of samples falling under ijth bin in case of two dimension will be nij. Okay. So, in 3 dimension, as we have defined this mean point and max point, here also you find that for the mean point I have the coordinates. Let us assume that x1 mean, x2 mean and x3 mean. These are the mean point of, this is the mean point of say kth bin. So, I put a1 x1k, x2k, x3k. So, this is the mean point of the kth bin. Similarly, max point I defined as x1 max as it is for the kth bin. So, x1k, x2 max k and x3 max k. So, this is the max point of the kth bin. Now, any point P at x1, x2, x3, if it has to lie within this kth bin in 3 dimension, I must have the condition that x1k mean must be less than or equal to x1, which must be less than x1k max. Similarly, x2k mean must be less than or equal to x2, which is less than x2k max, and x3k mean must be less than or equal to x3, which must be less than x3k max. If all these 3 conditions are satisfied simultaneously, then only I can say that this point P falls within the kth bin. For whichever bin this condition, all these 3 conditions are simultaneously satisfied, the point P falls within that particular bin. So, by using this, given a set of 3-dimensional vectors, I can find out that how many of these vectors are falling under which bin. Okay. So, if I find that nk number of vectors are falling under the kth bin and capital N is the total number of training vectors, then the fraction of vectors which are falling under this kth bin is given by nk by capital N. Okay. And now, the volume of the kth bin, if that is Vk, and the probability density in the kth bin, if that is say Pk capital X, I must have Vk time Pk capital X is equal to Nk by N. Now, here you find that I can find an analogy from one dimensional case or in two dimensional case. In case of one dimension, we said that the area under the probability density curve has to be equal to 1. In case of two dimensional case, we have said that the volume under the probability density surface is equal to 1, has to be equal to 1. Now, following the analogy over here, you find that this is my probability density value within the kth bin, and this is the volume of the kth bin. So, this being the density and this being the volume, I can say that Vk times Pks represents mass. So, the total mass under this probability density has to be equal to 1. So, this is a simple analogy which can be drawn from one dimension or two dimension to three dimension, and later on we will see after some time that this can be extended to multi-dimension. So, once I have this, my simple calculation is the probability density value within the kth bin of x, where x is my three dimensional vector. So, this x is nothing but a vector x1, x2, x3 which falls under the kth bin. So, the probability that a vector x will fall under the kth bin is simply given by Pkx is equal to 1 upon Vk times Nk by capital N, where Vk is the volume of the kth bin, Nk is the number of samples which is falling under the kth bin, and capital N is the total number of training samples. So, I can easily find out the probability density function in case of three dimension. Now, let us see that how we can extend this to multi-dimension, because as we have seen earlier, in our case it is not necessary that I will have only the scalar variable or vector variables, two dimensional vector variables or three dimensional vector variables and so on. The dimensionality of our vectors can be much more than that, because when we are dealing with pattern recognition, each vector is formed by different features of the pattern. I can compute one feature, I can compute two features, I can compute three features, I can compute 5 features, I can consider 10 features, I can consider 100 features, I can consider 1000 features. This depends upon what is the complexity of the patterns that we are trying to deal with. If the pattern is very simple, only one feature may be sufficient, in which case a univariate probability density function is sufficient for us. If the pattern is slightly more complicated, I may be satisfied with 3 number of features, which gives me 3 dimensional feature vector. So, probability density function in 3 dimension like this, what we have computed, that may be sufficient. If the pattern is very complicated, where I may have to have hundreds of features to represent a pattern, maybe 1000. So, those 1000 features forming a feature vector, the dimensionality of my feature vector becomes 1000. Okay. So, the space that I have to consider in which I have to estimate the probability density is neither 1 nor 2 nor 3, it has to be a 1000 dimensional space. And visualization of a 1000 dimensional space is not that simple. Maybe somehow we can visualize up to 3 dimension, but we cannot easily visualize a 1000 dimensional space. But what I have to do is I have to work using the concepts. Okay. So, before I go into that, let us just look at that how I can evolve a multi-dimensional space. Let us consider a very simple case initially. Suppose I have a point. So, this is a point, and we all know that a point is of 0 dimension. It neither has length nor breadth, no depth and so on. So, it has 0 dimension. Now, if I pull this point in a certain direction along a certain line, what I get is a line segment. And a line is in one dimension. So, you find that from 0 dimension, which was a point, if I pull the line in a particular direction, what I trace is a line, and this line is defined in a single dimension, because I know what is the direction of the line. Okay. So, what I have is a line is in one dimension, because I know what is the direction of the line. Okay. So, what I get is an one dimensional space, and a straight line is defined in a one dimensional space. Now, given this, if I now pull the line or drag the line in a direction perpendicular to the direction of the line, or in other words, I drag the line in this direction. Okay. So, I get the line over here. So, you find that what I have is a rectangle. So, from one dimensional space which contains a line, if I drag the line in a direction which is perpendicular to the direction of the line, what I define is a rectangle, and this rectangle is in 2 dimension. Okay. So, if this was one dimension, this is the other dimension. One of the dimensions I call as x1, and the other dimension I call as x2. So, I have a 2-dimensional space, and in the 2-dimensional space I have a rectangle, okay, or even a square, which is defined in a 2-dimensional space. Now, what I can do is I can drag this square or the rectangle in a direction which is perpendicular to the plane x1, y, x2. Okay. So, if I drag it in a direction which is perpendicular to x1, x2, like this. So, this was the plane. I have dragged this plane in the direction perpendicular to x1, x2. What I have got is this. So, now you find that what I have actually got is a cube, because if the displacements or the amount of drag in every direction is same, I get a cube. If they are not same, I get a parallelogram, and this parallelogram is defined in 3 dimension. Now, come to a case that when this point was dragged by an amount, say L, the length of the line becomes L. If I drag this line perpendicular to the direction of the line by the same length L, I get a square whose area is L square. If I drag this square in the direction perpendicular to the plane x1, x2, I get a cube. So, this is also L, and I get a cube whose volume is simply L cube. Now, if the amount of drags are different, suppose this drag is A, this drag is, let me some other color, this drag is A, the amount of this drag is B, amount of this drag is C. What I get is a parallelogram whose volume is simply A, B, C. Right. So, now let us use another concept, that I have a 3-dimensional space, and in the 3-dimensional space I have a cube or a parallelogram. Now, I can also assume that this cube or this parallelogram is something like a planar segment, a plane segment in a hyperplane. As we said that up to 3 dimension we say planes, beyond 3 dimension which we cannot visualize easily, we add the term hyper. So, I can consider that this cube or this parallelogram is a planar segment in a hyperplane. So, if I drag this cube in the direction which is orthogonal to the hyperplane, what I have is I have another cube or another parallelogram in 4th dimension. So, this is something conceptual. So, I have another cube or another parallelogram in 4th dimension, and if that drag is same as drags which we have given before, that is I drag it by the same displacement L, the volume of that hypercube in 4th dimension will be L to the power 4. So, what we have done over here, that in 3 dimension the volume of the cube is L cube, in 4th dimension this will be L to the power 4 if it is a hypercube in 4th dimension. Whereas, if I drag it by a displacement d along the 4th dimension, I get a hyperparallelogram in 4th dimension, and the volume of that hyperparallelogram will be simply ABC, which was the volume of the parallelogram in 3 dimension. In 4th dimension, it will be A, B, C, D. So, you find that the concept is very simple, and I always have analogy to lower dimensions. I may not stop there. I can consider this hypercube in 4th dimension is actually a planar segment in a hyperplane in 4th dimension. So, if I drag this 4th dimensional planar segment in a direction which is orthogonal to that hyperplane, I get another parallelogram in 5th dimension, and if that amount of drag is same as L, the volume of that hypercube in 5 dimension will be, instead of L to the power 4, it will be L to the power 5, and if the amount of drag is E in the 5th dimension, the volume of the hyperparallelogram that I get in 5 dimension will be A, B, C, D times E, where E is the amount of drag in the 5th dimension. And this concept I can go on extending in multiple dimensions. So, if I have a feature space of dimension say 1000, okay. So, the volume of a hypercube in 1000 dimensional space will be given by L to the power 1000, as 1000 is the dimension of the space. Okay? And this is a cube in 1000 dimensional space, where every side of that hypercube is equal to L. Considering from here, if A1 is the length of the hyperparallelogram in 1st dimension, A2 is the length of that hyperparallelogram in the 2nd dimension. Like this, A1000 is the length of that hyperparallelogram in 1000th dimension, then the volume of the hyperparallelogram will be A1 into A2 into A3 up to 1000. So, I can simply represent this as product AI, I is equal to 1 to 1000. So, this will be the volume of the hyperparallelogram in 1000 dimension. Okay. Now, whatever we do, as we have seen in case of 2-dimensional space or in case of 3-dimensional space, that every bin can be uniquely identified by the location of 2 vertices. One of the vertex is the min point, the other vertex is the max point, and for any point to lie within this bin, its corresponding coordinate must be greater than or equal to the corresponding coordinate of the min point and less than the corresponding coordinate of the max point. So, similarly, in this multi-dimensional space, what we are doing is this is basically either a hypercube or a hyperparallelogram in a multi-dimensional space. So, to uniquely identify a hypercube or a hyperparallelogram in a multi-dimensional space, if I have the coordinates of the mean point and the coordinates of the max point, that is sufficient. I do not need to store any other vertex, the information of any other vertex of that hypercube or hyperparallelogram. Okay. So, if I have the mean point and the max point, that is sufficient for me. So, given this, now I can write the conditions that say V is the max point, V is the mean point, and let us say W represents the max point of a volume element, whether this volume element is in 1 dimension or in 2 dimension or in 3 dimension, 4 dimension, 1000 dimension, 10,000 dimension, does not matter. I have defined what is my mean point and what is my max point. Okay. And suppose this is defined in say n dimensional space. N may be 1, it may be 2, it may be 3, it may be anything. This is in n dimensional space. And incidentally, let me mention that in n dimensional space, a cube, a hypercube in n dimensional space is actually called an n cube. Similarly, a hyperparallelogram in n dimensional space will be called n hyperparallelogram. Okay. So, these are the terms that we use. So, what I have is n dimensional space. So, accordingly, this mean point V will have n number of components. So, it will have V I for I 1 less than or equal to I less than or equal to n. So, different coordinates of the mean point. Similarly, for the max point, I will have different coordinates, which is given by W I, where 1 less than or equal to I less than or equal to n. So, once I have defined my mean point and max point, now suppose I have a point P. In ith dimension, the coordinate of this point P will be Pi. So, in ith dimension, or ith direction, coordinate is Pi. So, here again I varies from 1 to n as we have n dimensional space. So, P is an n dimensional vector as V or W, each of them are n dimensional vectors. So, if this P has to lie within the volume element or within the bin defined by V and W, I must have the condition that V I must be less than or equal to P I, the corresponding coordinate, which must be less than W I. Okay. And this has to be satisfied for all I within 1 to n. Okay. So, V I less than or equal to P I less than W I, V being the mean point and W being the max point. So, if this is satisfied for all I between 1 to n, that means for in every dimension the corresponding coordinate of P must be within the minimum limit and the maximum limit of the corresponding dimension of the hypercube. So, if this is satisfied for all I, that means for every coordinate of point P, then we say that point P is contained within the corresponding hypercube, or the corresponding hyperparallelogram. So, given this, now you find that estimating the probability density function or probability density value using the histogram technique in n dimension is as simple as we have done in case of 1 dimension or in 2 dimension or in 3 dimension. So, what I have to do is this n dimensional space has to be divided into a number of bins or cells, where every bin or every cell will be of dimension n. Okay. So, this will be divided into a number of bins or number of cells in n dimension. Then when I have a set of training samples or the training vectors, so every training vector is of dimension n, I have to compute that how many of these training vectors falls under say kth bin, where this bin is an n dimensional hypercube. And I identify whether a vector falls in this kth bin or not simply by using this condition, that the mean point of the kth bin and the max point of the kth bin. So, every coordinate of the feature vector must be greater than or equal to mean point of the kth bin, the corresponding coordinate of the mean point of the kth bin, and it must be less than the corresponding coordinate of the max point of the kth bin. So, by this I can identify that how many of these samples falls under the kth bin. And then the fraction of samples which falls under the kth bin is simply nk upon capital N, okay, where nk, if I assume that it is the number of samples which falls under the kth bin, and capital N is the total number of samples. So, this fraction of samples falling under the kth bin divided by the volume of the kth bin, where volume of the kth bin is simply either L to the power n, because we are using n dimensional space, or if it is a hypercube and L being each side of the hypercube, or ai, take the product I varying from 1 to n if it is a parallelogram. Okay. So, after all, it is the fraction of the samples which falls under the kth bin divided by the volume of the kth bin that gives me the probability density estimate within the kth bin. So, a sample will fall within that kth bin with a probability density as estimated by this method. So, overall what we have is, if pk is the probability that a sample falls under the kth bin, it is simply 1 upon Vk, where Vk is the volume of the kth bin, or W and V are getting, sorry, let me put it other way. So, P, instead of P, let me call it Q, because we are using P to represent the point here. So, Qk, which is the probability that a sample falls under the kth bin, is simply given by 1 upon volume K, which is the volume of the kth bin, into say let me put it as say Rk upon capital R, where Rk is the number of samples in kth bin, and R, this is the total samples, total number of samples. Okay. So, whether we are trying to find out trying to estimate the probability density function in 1 dimension, 2 dimension, 3 dimension, n dimension does not matter. The concept is this: I can use it in 5 dimension, I can use it in 10 dimension, I can also use in 100 dimension, does not matter. Okay. So, this is what we have discussed about the histogram based technique for probability density estimation. We said initially that there are many other techniques, but the other technique that we are going to discuss in this course is what is called window based technique. So, the next technique that I will discuss now is what is called window Now, what is this window based technique? In case of window based technique, it is assumed that every sample is a representative of a probability density function. Okay. So, this representative can be a delta function or it may be any other window function. However, our constraint is that the total area under this probability density curve that we are going to estimate, that must be equal to 1. Okay. So, if I use a delta function, a very simple case, if I use that probability density function is a delta function and every sample represents the probability density function which is a delta function. So, what is a delta function? It is a spike with a very small width, right. And as before, the area under this delta function will be the width multiplied by the height of that spike. Okay. So, if I have situation something like this, that I have say, let us assume that we have only 3 samples, 1, 2 and say 4. So, these are the 3 samples that we have. Obviously, in this case we are assuming that we have a scalar variable x and these are 3 samples of the scalar variable. So, if I use, so this is my x and this is this direction I plot probability of x. So, I have a sample, this is 0, this is say 1, this is 2, somewhere here it is 3 and this is 4, this is 5, this is 6 and so on. And as I said that every sample is a representative of a probability density function. So, initially if I assume that that representative is probability density function is a delta function, something like this. So, I have one delta function at location x equal to 1, I have another delta function at location x equal to 2 and I have another delta function at location x equal to 3. And as we said that our constraint is the total area under this probability density function has to be equal to 1. So, that clearly says that area of this delta function has to be 1 by 3, area of this delta function has to be 1 by 3, area of this delta function has to be 1 by 3. Now, if I have a situation something like this, that my samples are 1, 2, 4 and I have one more sample at location 1. Then obviously, there are 2 delta functions which will be superimposed at location x equal to 1. So, the height of this delta function will be just double. And not only that, area of individual delta functions has to be 1/4. In the earlier case, I had only these 3 samples. So, the area of individual delta functions was equal to 1/3. So, that when I add all of them together, all these delta functions together, the total area becomes 1. But now I am considering a case where I have 4 delta functions, okay, because I have 2 samples lying at location x equal to 1. So, I have to have 4 delta functions and the total area has to be equal to 1. So, the area under every delta function has to be 1 by 4. So, I have a situation something like this, area of the delta function at x equal to 1 has to be double of the area of the delta function at location x equal to 2 or area of the delta function at location x equal to 4. Total area has to be equal to 1. Now, if I have this sort of situation, then you find that this is not really approximating a continuous probability density function, because what I'll have is I'll have a set of spikes, a set of disjoint spikes. So I am not really estimating a continuous probability density function. But what I have to do is I have to use a continuous, I have to estimate a continuous probability density function from the set of samples which are given. So the delta function to be a representative probability density function is not really suitable. Instead of delta function, I can use some other functions called window functions or kernels, which can help us to estimate the continuous probability density function in a smooth way. So what we will use is window functions or which are also called kernels. Of course, they have to be properly normalized so that the total area remains equal to 1. So these window functions or kernels again can be of different type. I can use a very simple rectangular window. I can use triangular window. So the window, if I use a rectangular window, the window will be something like this, which is nothing but a box function. If I use a triangular window, the window will be something like this. Or even I can also use a normalized normal distribution. So the window will be something like this. So different types of window functions or different types of kernels can be used to estimate the probability density function. So find that over here, when I have a situation that I have 3 samples at location 1, 2 and 4, the situation was something like this. So if I use say simpler case this rectangular window, then at 1 I will have a rectangular window. Suppose the width of the window is, let us assume 2. So I place a window 2 over here. At location 2 again I have to put a rectangular window whose width, let us say again equal to 2. So this window will be something like this. And at location 4 again I will put a rectangular window whose width is again equal to 2. So I will have a window something like this. So the overall probability density estimate is basically sum of all these window functions. And I have to normalize these windows in such a way that because I have 3 different windows, so the total area under these 3 different windows has to be equal to 1. Okay? And by using this, you find that your overall probability density function, as it is the sum of all the probability density estimates, will be something like this. Okay. So this curve gives me what is the probability density estimate P of x. Right. So right now what we have done is something visually. In the next class, we will talk about if I use instead of rectangular window say a triangular window or some other window, how can we estimate the probability density functions, right? And we will also find analytically that how we can estimate given these different samples, say 1 to 4 or something like this, these different samples, and given the kind of window function that you are going to use, then how we can estimate the probability density at an unknown location x. So I want to estimate this P x, where x is not any of these samples which are given for training. Okay. So these samples are given, you are given an window function which has to be used to estimate the probability density. Now, at an unknown x, I want to estimate what will be p of x. So, how we can do it? By using the window function. So, that part we will consider in our next class. Thank you.